Today I'm going to talk about integrals involving trig substitutions. So if you haven't done so already, print out these notes. Go ahead and pause the video and go to my website and find these notes and print them out so you can follow along. Then unpause it and we can continue. So integrals involving trig substitutions are different than integrals involving trigonometric functions. Here I'm talking about integrals that don't obviously involve trigonometry, but rather involve square roots of quadratic-looking expressions with x squared under the radical. Something like a number squared minus x squared or plus x squared or something of that nature. And it doesn't look like it's going to involve trig. But in fact, that is the right technique to use. You introduce some trigonometry according to the following chart. So if an integral, for example, has something that looks like square root of a number squared plus x squared, you make a substitution x equals a tan theta, where a is the number that's squared. And why would you want to do that? And why am I calling it reverse trig substitution? Well, when you use u substitution, you're usually substituting something like u as a function of x. But here we're substituting x as a function of u, or in this case theta. So it's almost a backward substitution that initially makes the integral look worse than it was to begin with. But by the magic of trigonometry, you can use a Pythagorean trig identity to simplify everything, like sine squared plus cosine squared equals 1, or one of the other ones. Now, why does this work? Right triangles. So I'll give you an example, which I can squeeze in here. If you draw a right triangle, with this angle being theta, and this being the right angle, let's look at this first case, for example. Suppose we label the sides x and a. Well, by the Pythagorean theorem, this hypotenuse should be the square root of a squared plus x squared. Also, the tangent of theta would be opposite over adjacent, x over a, which is this. X equals a tan theta is the same thing. So there is a relationship between x equals a tan theta and some expression like square root a squared plus x squared, which you can see both exhibited on this one triangle. And we're actually going to use right triangles to do these problems. One more little tip, a little caveat about these integrals. Sometimes the radical doesn't look exactly like this. Sometimes there's an extra term involving just x in addition to an x squared term. In that case, you might have to do a little algebra, like completing the square or making some kind of u substitution or both, in order to force the radical to look exactly like one of these three cases. And I'll do an example of that in a minute. So let's do a first example of an integral involving a trig substitution. Here we have integral dx over square root 4 plus x squared. So your clue that it needs a trig substitution is that it has something like this, a square root with an x squared under it. And indeed we're in this first case where a here equals 2. 2 squared plus x squared is what's under the radical, suggesting we should make the substitution x equals 2 tan theta. So let's do that. If x is 2 tan theta, we're going to have to find a substitute for dx in order to write this whole thing in terms of theta. So what is the derivative of x? If x is 2 tan theta, the derivative is 2 secant squared theta d theta. So again, for these, you kind of have to have those trig integrals and derivatives memorized. Now let's change this integral to thetas instead of x's. And again, like I said a minute ago, initially it's going to look worse, but I promise it will get better. The dx on the top, when changing to thetas, becomes this ugly thing, 2 secant squared theta d theta. Much uglier than just dx. And on the bottom, you get square root of 4 plus x squared. Well, x is 2 tan theta, so x squared would be 4 tan squared theta. So, let's see. It looks like it's bad, but this is the point where we have to use one of these Pythagorean trig identities to simplify. And here we're going to use this second one. Tan squared theta plus 1 equals secant squared. This thing, 4 plus 4 tan squared theta, is just 4 times as much as 1 plus tan squared theta. So it should be equal to 4 secant squared theta. So let's do that and see what happens. The top stays the same, and on the bottom we get 4 secant squared theta. Well, you probably see what's going to happen. The square root of 4 is 2, and the square root of secant squared is secant. So the square root goes away, and we just get 2 secant theta, and we get some beautiful cancellation here. The 2's go away, one of the secants goes away on the top, and you just get the antiderivative of secant theta d theta. Now, this you have to have memorized, which I had said in a previous lecture and page of notes, you should have that memorized. It is natural log of the absolute value secant theta plus tan theta plus c. So now it is time to change back from thetas to x's because the original problem was about x's, not thetas. So let's go ahead and do this. Well, this presents a little bit of a problem because, well, tan theta we can do, right? X is 2 tan theta, so tan theta must be x divided by 2. But what about secant theta? What is that? This gives no indication directly of what secant theta is in terms of x. So what you have to do is draw the right triangle. Same as we drew on the previous page. We have to draw the right triangle that expresses this relationship, x equals 2 tan theta. So back up here at the top, let's draw this. If x is 2 tan theta, then tan theta, as we said, is x divided by 2. So your picture might look like this. Here, convince yourself the tangent of theta is x over 2. Then we want secant theta. That involves the hypotenuse. So let's figure out the hypotenuse from Pythagorean theorem. We should have 2 squared plus x squared is the hypotenuse squared. So we get 2 squared plus x squared under the square root. Now, you'll notice square root 4 plus x squared matches the square root 4 plus x squared in the original question. That's a good sign. That means we're on the right track and we're doing it correctly. So let's look at this picture here. We want secant theta. What is secant of theta? That would be the hypotenuse over the adjacent. It's the reciprocal of cosine. So it's the hypotenuse over the adjacent. And now we've done it. We now have secant theta in terms of x, which we put back in here. Square root 4 plus x squared over 2. And now we're done. And we can circle this and be done. However, if this was a homework problem and you look it up in the back of your textbook, you might see that the 2's are missing. So what happened to the 2's? Well, this answer is correct, but there is a way to just throw out the 2's. Now, how can we do that? Well, by rules of logarithms, watch what happens here. First, put everything over a common denominator. And then reason that the log of a quotient is the difference of the logs. So you have to kind of dust off your knowledge of logarithms. Remember this, the natural log of p over q is the natural log of p minus the natural log of q. And this thing, negative natural log 2, that's just a constant, like negative 0.69 something. So this constant can be swallowed up with this constant and just called some new constant, let's say c1. So what happens is in effect, the divided by 2 has just disappeared, and that's your final answer. Natural log square root 4 plus x squared plus x plus some constant. Let's do one more example of an integral involving a trig substitution. You know this integral involves a trig substitution because it has a square root with an x squared and some other junk under the radical. The problem is that it doesn't look exactly like one of these cases. So this is where this little caveat comes in, where it says if there's an x term in addition to an x squared term, you have to do some algebra, like completing the square or making a u substitution to force the radical to look like one of these cases. So let's see what happens. Well, we have to complete the square here. So x squared plus 4x, it should be plus 4. But to make it minus 5 total, we have to say it's plus 4 minus 9 to make the minus 5, in which case now we have it as x plus 2 quantity squared minus 9. Now this does look like one of these cases. It's a number squared plus a variable squared. And in this case, our variable is x plus 2. And if that's really confusing to you, you could do a u substitution at this point, u equals x plus 2. But I'm going to skip that step and instead just work with the x plus 2. So our variable here, let's see, which case are we in? We're in the x squared minus a squared type case. So that's this case. We should substitute x equals a secant theta. So we get, actually instead of x, our variable is really x plus 2. So our x plus 2 should be a secant theta. Our a here is 3 because of the 9. Again, if it's confusing to you to assign the x plus 2, you could always use a u substitution as an extra step. But I'll do it this way. The derivative on this side is just dx, and on this side, the derivative of secant theta is secant theta tan theta, d theta. So let's change this whole thing to thetas. X on the top, well, if x plus 2 is 3 secant theta, then x is 3 secant theta minus 2. Our dx, also on the top, is this whole mess, 3 secant theta tan theta d theta. And on the bottom, we have x plus 2 squared. Well, if x plus 2 is 3 secant theta, then x plus 2 squared is 9 secant squared theta minus 9. And now it looks worse than ever. So it's time to apply some Pythagorean trig identity. And in this case, we want something that looks like this. If we subtract 1 from both sides of this, we get tan squared equals secant squared minus 1. And this is exactly 9 times that big. This is 9 secant squared minus 9. So according to this, this should be 9 tan squared theta. Now, if this really says 9 tan squared theta and we're taking the square root of it, the square root of 9 tan squared theta would be just 3 tan theta. So I skipped a step there, but if you want, you can add in that extra step. And I'm going to copy the top as it was. And now look at the cancellation, the 3 and the 3, the tan theta and the tan theta. And if we distribute this, we get 3 secant squared theta minus 2 secant theta. Now, let's see what happens now. The antiderivative of 3 secant squared theta, you can see directly, if you have it memorized, is 3 tan theta. The antiderivative of 2 secant theta is a little more complicated, but again, to do these efficiently, it's worth memorizing the antiderivatives of things like secant. And that's natural log secant theta plus tan theta. And we throw on our plus c. Now, our original question is not about theta, but it's about x. So we have to go back here to see how x and theta relate. And we don't only have secant, we also have to figure out stuff about tangent. So again, as in the previous example, we should draw a triangle that captures the situation. If x plus 2 equals 3 secant theta, then secant of theta is x plus 2 divided by 3. That means that the hypotenuse over the adjacent is x plus 2 divided by 3. So this situation, this triangle captures the situation, and you can convince yourself that indeed the secant of theta is x plus 2 over 3, which is the same as this. Now we want to know about tan theta, which involves the opposite side, so we need to figure this out with Pythagorean theorem. So you could call this b, this side b, and say 3 squared plus b squared equals x plus 2 squared, and solve for b. But what you're going to find out is that after all the dust settles, b is square root x squared plus 4x minus 5, which is a good thing because that's an expression directly from our original question, showing that we're on the right track. So now you can read off what is tan theta. Tan theta, according to the triangle, is opposite over adjacent. This square root divided by 3. Minus 2 natural log secant theta, that we can take directly from here. It's x plus 2 divided by 3. And then tan theta, again, similar to here, is square root x squared plus 4x minus 5 divided by 3 plus c. And let's just clean this up a little bit. Like the 3's cancel, giving us x squared plus 4x minus 5. And then, as in the previous example, go back and look at that if you forgot what we did. But it turned out that by rules of logarithms, the 3's in the denominator here just disappear. So we get this. And now we are done. So these are long problems, and they might be a little intimidating, but after you do a few of them yourself, you'll get the rhythm of them. So my suggestion is that you do these 3 on your own, and then you'll be ready to do the homework that's been assigned.